Today we will discuss about Myhill Nerode relation. So first we start by discussing about equivalence relation. So any relation R defined on set A can be considered to be a subset of A cross A, and the relation for the relation R to be an equivalence relation, it has to be reflexive, symmetric and transitive. So by reflexive, what we mean is every element A, element of capital A, should be related to itself. By symmetric, what we mean is for A and B elements of A, if A is related to B, then it also is true that B is related to A. R is transitive for the elements A, B and C element of A. If A is related to B and B is related to C, implies that A is related to C. So when we talk about equivalence relation, what we can see is that the equivalence relation partitions the set A into disjoint equivalence classes. So equivalence relation on set A partitions A into disjoint non-empty equivalence classes. And as an example, we will consider the relation congruence modulo integer m, and we use the identity symbol to denote the equivalence relation. So the relation is defined on set of integers, and we say that we say integer I is related to j if I minus j is divisible by m. And if we consider m to be 3, then we can see that the set of integers is partitioned by this equivalence relation into three equivalence classes, and the three equivalence classes are shown here. So now coming back to Myhill Nerode relation, what we can see is that two strings x and y element of sigma star are related by an equivalence relation on the DFA M if from Q0 on reading X we reach the very same state as we reach by reading Y starting from Q0. That is, two strings X and Y are related if we reach the very same state starting from the start state in the case of a DFA. And some of the properties of Myhill Nerode relation are that it is right congruent. That is, if we take two strings x and y, which are element of sigma star, and if x is related to y, it implies that xa is also related to ya. That is, we are appending a on the right hand side of strings x and y, and the strings so generated will also be related. So that is very evident. So after reading x and y, we are reaching the very same state, and from that state, if you read another symbol a, we will be going to the very same state in the case of a DFA. So that is very evident in the case of a DFA. Now next is it refines R. So now if you look at a regular set, which is a subset of sigma star, then the elements of the regular set are such that it represents all the strings which are accepted by the finite state automata. And when we define an equivalence relation over the DFA, we can see that some states are non-final and some states are final. And now, if we take the union of all the final states, then it will represent the set R. And if we take union of all the non-final states, then it will represent sigma star minus R. So when you talk about R, it represents strings that are accepted by the finite state automata. And when we define an equivalence relation, what is happening is it is refining it. So when we say refining it, what is happening is uh, within a set of elements, again we will be able to partition it into subsets. That is, there might be more than one final state, and each of these final states will be representing a class of strings uh, by themselves. And in the case of final states, when you take union, you get the set R. And in the case of non-final states, if you take union, you will get sigma star minus R. And next property is that the equivalence relation will be of finite index. That is also very evident in the case of DFA. That is, if suppose X is an element of sigma star, then when we read X, we will be reaching some states. So the set of states that are reachable is finite, because a finite state automata has got a finite number of states. So the number of equivalence classes is finite because each and every state represents an equivalence class according to this particular definition for the equivalence relation. So if all these three properties are satisfied, then an equivalence relation is also called to be a Myhill Nerode relation. So now let us see what we mean by this with respect to a DFA by taking an example. So we have taken a DFA here, and this DFA, what it represents is, it represents the strings that end with BB. So every string that ends with BB is being accepted. So here Q0 is a state that denotes that we have to see BB to go to the final state. So we have not seen anything that can be considered to be part of the last two symbols, which should be B followed by another B. So Q1, what it represents is, it represents a possibility that the last symbol that we have seen is B, and if the next symbol is B and there are no more symbols following it, then we should be accepting it. So Q1 is a state that signifies that for the substring that we have read so far, the last symbol is B, which could be part of the last two symbols being BB. And the state Q2, what it signifies here is that the last two symbols that we have read is B, and so we are in state Q2, which is an accepting state. So if there are no more symbols, then we will remain in Q2. And now we will look at failure in the case of each and every state. If in Q1, if we come across A, then we have to see two more B's coming consecutively in order to reach the final state. So in Q1, if we read another A, we will go to state Q0. And in the case of Q2, if we read an input symbol A, we will be going to Q0, because again we have to see two more B's which appear adjacent to each other to come to Q2. And in Q2, if we are reading another B, in that case also the last two symbols that we have read are B followed by B. So in that case also we will remain in state Q2. So for this particular DFA, now since we have got three states, we can partition strings which is represented by sigma star into three equivalence classes corresponding to state Q0, Q1 and Q2. So the equivalence class corresponding to Q0, it will denote all those strings that will end up in Q0. The equivalence class corresponding to Q1 will represent all the strings that will end up in Q1, and the equivalence class for Q2 will represent all the strings that will end up in Q2. So an equivalence class can also be represented using any of the strings that is member of that equivalence class. So here for the equivalence class represented by Q0, I have used the string A to represent it. So the equivalence class represented by string A will contain as members epsilon, A, AA, BA, AAA, and so on. So now the equivalence class represented by Q1 is represented by the string B, because B itself is a member of that equivalence class. And now that equivalence class will contain the strings B, AB, AAB, BAB, and so on. Now the equivalence class corresponding to Q2 is represented by a member of that equivalence class. We are taking BB in this case. So the equivalence class represented by BB will contain the strings BB, ABB, BBB, and so on. So here, if you look at say the equivalence class corresponding to BB, so we can see two strings. Let ABB, we will take it as X, and the string BBB, we will take it as Y. So here we can say that X is related to Y, because when you read ABB starting from Q0, you end up in Q2, and in the case of BBB also, you end up in Q2. So in that sense, every two strings that are element of this set are related to each other. Also, every string is related to itself. Now, Myhill Nerode theorem, what it states is that languages is regular if and only if the number of equivalence class corresponding to that language L is finite. So we can use this Myhill Nerode theorem to show that certain languages are not regular. So let us take an example: 0 raised to n, 1 raised to n. So, according to Myhill Nerode theorem, if it is regular, then the number of equivalence class has to be finite. So, let us assume 0 raised to n, 1 raised to n to be regular. So, in that case, the number of equivalence classes should be finite. So, it should be so each and every state denotes uh, an equivalence class. So, the number of states should be finite. So let us. So what we are going to look at is can uh, can we have different states when we read different number of zeros? So that is not possible, because the number of states are finite. So there has to be a string 0 raised to j and 0 raised to k, such that when you read 0 raised to j and when you read the string 0 raised to k, you end up in same state qi, because number of states are finite. So from qi, if you read I raised to j, you will be reaching a final state. From qi also, when you read the string 1 raised to k, you will be reaching a final state, because 0 raised to j, I raised to j is a string of 0 raised to n, 1 raised to n. Also, 0 raised to k, 1 raised to k is also an element of the language 0 raised to n, 1 raised to n. So, but the problem is when we read the string 0 raised to j followed by 1 raised to k. Also, when you read the string 0 raised to k followed by I raised to j, what is happening here is you will be reaching the final state. So, 0 raised to j and 0 raised to k are not of the form 0 raised to n, 1 raised to n. So, we can now say that this particular finite state automata is not accepting the strings of the form 0 raised to n, 1 raised to n. Okay. So now there is a contradiction. So according to our assumption, a this was a regular language. So since we assumed it to be regular language, we assume that the uh, the number of equivalence classes are finite. So that is not possible with respect to the language 0 raised to n, 1 raised to n. So in this case, we can use Myhill Nerode theorem to show that certain languages are non-regular. So the next topic that we will discuss is homomorphism. So homomorphism is another property about regular languages, and it turns out that regular languages are closed under homomorphism. So now homomorphism is basically a substitution function. So we will use H to denote the homomorphism. And here what is happening is we are substituting each and every symbol element of sigma with a single string. So you have 0 which is an element of sigma, you are substituting it with a single string. So you have 1 which is an element of sigma and you are substituting it with another string c. So H is now applied to symbols of the alphabet set. We can also extend it to a string. So suppose A1, A2, A3, etc. An is a string where A1, A2, An are symbols from the set sigma. Now we have taken a string A1, A2, etc. An, and now when you apply the homomorphism on this string, uh, it is same as performing homomorphism on A1 concatenation, performing homomorphism on A2 concatenation, performing homomorphism on A3 concatenation, and so on, performing homomorphism on the symbol AN. Okay, so now let us see what we mean by this with respect to an example. So here we have defined an homomorphism where homomorphism of 0 is AB, homomorphism of 1 is C. Now you can apply this to a string, and there what you are doing is basically you will apply homomorphism on 0 and you will concatenate with homomorphism of 1. You will concatenate it with homomorphism of 0 and so on. So basically what you do is you are substituting these symbols from the alphabet set with the corresponding strings, and this is the string that you generate by applying homomorphism on the string 0 1 0 1 0. So now we can convince ourselves that homomorphism is closed in the case of regular languages. So if a language is regular, we know that there should exist a regular expression. Suppose we consider the language 0 1 star plus 1 0 star, then we can come up with a regular expression for the set of strings that we get by applying homomorphism on the strings corresponding to this particular regular expression. Okay, so when you apply homomorphism to this particular language, you get uh, another language or set of strings, and those set of strings are again regular, and you can come up with a regular expression for those strings by substituting the individual symbols of the original regular expression with the corresponding string. So when you do this, you might have to introduce parentheses. So corresponding to the regular expression 0 1 star plus 1 0 star, what we do is we substitute for each and every individual symbols. So when you substitute for 0, you get AB. When you substitute for 1, you get C. So corresponding to 1 star, you get C star. Now plus for 1, you substitute with C, and it is 0 star, and since 0 is represented by AB, we have to introduce the parenthesis, so it will be AB within parenthesis star. So now you get regular expression which is equivalent to the language that you get when you apply the homomorphism on the language L. So, this since this regular expression represents applying H on L, we can say H of L is also a regular language. Okay, so that is with homomorphism.